We are.
All right, let's go. Hey, everyone. It's my pleasure today to introduce Kiran Menon, who some of you hopefully have met. Kiran is a first-year graduate student here in our program, but no stranger to graduate school because Kiran has a few degrees and somewhat a non-traditional path to get to where we are today. But I think it gives him quite a bit of insight and strength into the kinds of work that we'll be getting into for his PhD. What you're going to hear about today is a little bit about some of the work that Kiran did just prior to coming here, which was while doing a master's degree with Sandeep Pal of Texas Tech. But just by way of introduction, here are a few things you may or may not know about Kiran. Did you know that he's a brown belt in karate? He's sport climbing certified. He wrote a novel called Inner Conflicts. He's a pretty powerhouse person. And more important than that was before coming into quiet film. Before actually coming into atmospheric science, actually had a whole second life and career really focused on computing and programming. And so original degrees in India were a Bachelor of Technology in Electronics and Communication Engineering, followed by a Master's in Engineering in Communication. And then afterwards worked for Infosys, right, for almost a decade. As a software developer that worked in all sorts of things in Unix and JavaScript and SQL and MATLAB and everything else that were things that were attractive to me as a lab of thinking about, oh, here's somebody who's done a lot of work already in thinking about computational systems and now wants to apply it to interesting things, in my opinion. And so after that career working as a technology lead in Infosys in India and also in Singapore, came to Texas Tech to study boundary layer meteorology, which is what you'll hear about today. This was also an interesting degree. So Kiran's master's is not just in atmospheric science. It's actually an interdisciplinary degree in atmospheric science, wind energy, and English. And so you'll see this a little bit in the communication styles and the experience of how Kiran brings more creative side to our work as well, his work as well. And so I'm really excited to hear a little bit today about some of this work on boundary layer moisture variability under synoptically active and benign conditions over dryland ecosystem in the southwest US. I'll turn it over to you. Thanks.
Thank you for the introduction, Amber. And can everybody hear me fine? Great. So I'm excited to be here today to present my work on the boundary layer moisture patterns over in Dryland in West Texas. And like Ankur mentioned, this is my work that I did as part of the MS degree, along with my former advisor, Dr. Sandeep Pal at Texas Tech University. So let's dive in. So we will start with the question of why we care about the Dryland ABL moisture. So to set the context, we will define the atmospheric boundary layer. So as you might know, it's the lowest layer of the Earth's atmosphere, and it's directly influenced by the surface forcings. And the height can vary depending on the geographical location, the season, and other weather conditions. And you can see a schematic over there. And next, we have the Dryland ABL ecosystem, but there's not a lot of research done in that area. For instance, there's much work done on coastal regions, and a lot of work focused on large cities, but not enough on smaller cities like Amarillo or Lubbock. So that's one reason we chose this area. And moisture patterns are important. So far we haven't found any literature on that. So we hope to close this research gap. So as you know, water vapor initiates convective processes because it's less dense than dry air, and it's part of the hydrological cycle and is linked to extreme weather. And drylands are sensitive to climate change because of the water availability. And this paper Huang et al. Gives a good set of reasons for this sensitivity. One among those is transitional climate zones, which a lot of semi-arid regions are in. So that's a transition between dryland and agricultural land, for instance. And there is a difference in the dust aerosol cloud interactions. All of this will affect the drylands. And it houses 1/3 of the global population. And our study sites are in semiarid regions, which also houses about 15% of the population. And most of these people live in developing countries. So as you know, a lot of people in the developing countries are disproportionately affected by climate change. So if you look at the schematic, to move on. Here are the overarching objectives of the study. First, to develop an understanding of these ABL moisture patterns and the various conditions. And secondly, to improve the parameterization selection for numerical weather prediction in Drylands. So again, we don't have specific regimes for Dryland weather forecast. So in case you're not familiar, numerical weather prediction uses the governing equations along with numerical techniques. So there is of course a trade-off between accuracy and computational resources required. So we linearize the equations and we set the parameterization. Parameterization basically is modeling the effects of features that are in the subgrid, within the grid of modeling them. So the better information we have about these parameters, the better it is to forecast. And there are different parameterization schemes like microphysics, and we have one for ABL. So it's in WARF software is called PBL scheme, planetary boundary layer scheme, and that is usually a source of error in forecast. So we're hoping that our work will help with some of this parameterization selection. Like, for example, you can select the dry entrainment or moist entrainment regime, depending on the weather conditions. And lastly, we apply a hierarchical clustering technique to classify the different ABL moisture and other features. So we start with these hypotheses. Water vapor initiates convection, so we think that more water vapor in the boundary layer would increase the boundary layer depth. But also within the same season, assuming the other conditions are somewhat similar, we expect some dilution effects where the mean water vapor mixing ratio decreases with the increase in BLD, the boundary layer depth. So people usually talk about the dilution effects of aerosols and pollutants, but we don't talk about the water vapor, so we'll find out. Next, the wind direction. So we hypothesize that the southeasterly winds will result in an increase in the ABL moisture because to the southeast of these sites we have the Gulf of Mexico, and those winds carry moisture to our sites. And especially in the summer, there is a high pressure node, the secondary node of the seasonal North Atlantic subtropical anticyclone that's present in the Atlantic Ocean. That high pressure also creates southeasterly wind pattern, which brings in moisture laden air. So conversely, northerly and westerly winds should reduce the ABL moisture and its depth because these originate inland and they bring in dry air. And lastly, the higher near surface temperature change, that is the 2 meter temperature change, dt over dt, should increase the ABL. Because the difference in temperature should create more thermals and increase the boundary layer depth. So we study two sites in West Texas. So please note the terms BLE, WVMR and DT over DT. We will be talking about this quite a bit. So moving on to the data and methodology. So we have two sites, Amarillo and Midland, which are marked in the map. And we use the IGRA radiosonde sounding data. So as you know, there are 2 soundings per day at 0 UTC and 12 UTC. So we use the 0 UTC sounding to get the data boundary layer. But that is actually the transition between the daytime convective boundary layer and the nighttime residual layer. Because 0 UTC is around 7 p.m. or 6 p.m. In our sites, local time. And we have 6 years of data. So it starts from December because we're going from winter to fall. And we have other surface temperature and soil moisture and other synoptic conditions from the Menon and surface maps. these are the variables that are gathered from the radiosonde and a few that are calculated. We will look at a few of these in more details, the last three. This is our whole process. So we have all the input data and it's different, from various sources. And then we build the vertical profiles of thermodynamic variables like the mixing ratio and potential temperature, and then the near surface forcings like the temperature change in soil moisture, and the bulk Richardson number to calculate the VLD, and we account for some of the synoptic conditions, and the spatial temporal variability of these give the effect of seasons and synoptic conditions on the ABL moisture. And the bulk Richardson number helps us study the atmospheric stability. And we do a little comparison between the VLD estimation methods, so we have three. And the objective of this exercise is to find the basic features and then also get the input variables for the hierarchical clustering to get our different clusters based on the distinct features. So all of this would address the research gap in Dryland ABL and also help with selecting the right ABL parameterizations for an ABL. Let's look at a daily profile. So this is the mixing ratio, and we use the 200-meter vertical resolution and average the values within each 200 meters above ground level. And so we have each level, and the ABL top is usually where the transition occurs, but it may be hard to see on a heat map. And some of these observations are missing, so you will see some gray squares, and those are not interpolated for the heat maps. But for the purpose of calculating the bulk Richardson number, we do interpolate the values. And for the clustering, we use all the available values to calculate the mean and such. Next, we have the diurnal near surface temperature change. So this is a 2-meter temperature during the peak diurnal period. So this is a new method that my advisors group developed, and there's a paper published that uses this as one of the 3 variables to evaluate NWV model biases, and it's also used to estimate and classify satellite error biases. So we look at this profile, and we have the sunrise and sunset times, and let's define the peak period as sunrise plus 1 hour to sunset minus 4 hours. And then in this period we calculate the slope. So this offset can vary. It can be sunrise plus 2 hours, for instance, so it depends on what works best. And this temperature change is influenced by clouds and fronts. It can be negative if, say, a cold front passes. And this astral Python module has been very helpful to me to get the sunrise and sunset times in UTC. And to get the slope, I use the first order polynomial effect on Python. Next, we have the bulk Richardson number. So you may be familiar with this. It's a measure of atmospheric stability, and you can estimate the BLD using the critical value. So it's the BLD is defined as the first point vertically, where the bulk Richardson number reaches a critical value. So we have used 0.25 from past works, but you can adjust that parameter. So looking at the formula, you can see that it's proportional to the virtual potential temperature gradient and inversely proportional to wind magnitudes. So a higher gradient and lower wind magnitudes would mean a stable atmosphere, and opposite would be a turbulent one. So we have the boundary layer depth estimation from thermodynamic variable profiles. So we have used 2 here. The theta and the WVMR. So the second and last plot are the smooth versions. So it looks almost the same because this is not a complicated profile. Here again, the boundary layer height is defined as the first point vertically where the gradient occurs. So for potential temperature, it's the positive gradient, and for water vapor mixing ratio, it's the -1. So in case of complicated profiles, I iterate a few times to converge on the value. And then I will exclude surface inversions and local maxima to get the right boundary layer depth. And next we come to the main part, the hierarchical clustering. So this is a method used a lot in biology, in the study of genes, for example, where a large number of genes have to be classified. So it has also been used in weather studies, like the Duffer et al., which I followed. So we have various input variables, and then we pass it to an algorithm to scale the data set and to exclude outliers, and then the algorithm performs an agglomerative clustering technique, and we get different clusters which are separated in space, separated in a multi-dimensional space, where each of the variables forms one axis. And there is a Python module for that. So we'll look at that in a little more detail. So the agglomerative clustering is a bottom-up process. So the points at the bottom of the graph are individual data points, and you go from the bottom up until and club together points until you get the required number of clusters. And we have used complete linkage to estimate the distance between clusters. So this method uses the maximum distance between any 2 points, 2 clusters. So there are other methods using the average distance or the minimum distance. So this is selected based on how the clusters turn out. Like you shouldn't have one very large cluster and another cluster with 2 or 3 points. So somewhat uniform distribution is better. And I've been asked to elaborate on the multidimensional space before, so we'll look at this. So imagine a point in the 3D space, so we all know this. So how do you add a 4th spatial dimension? It's hard to visualize, so the way I think about it is, if you have another variable called R, so you have an axis, so it could have positive and negative values, and for each point on R, you define a corresponding point x, y, and z set of coordinates. So we have this. And then now you have 4 coordinates defining each point. And to add another dimension, you just repeat the process. So you have 5 of these. And to visualize it, a bubble plot is one way, where you have the size of the bubbles proportional to the magnitude of a variable, and then the color represents another variable. So you have 5D encoded into one figure. And now we can calculate the Euclidean distance, so no matter how many dimensions you have, and that is what is used in the complete linkage that we saw earlier. And a little digression. Now you have, imagine you have a cube, and this is just a cube with the edges, and it's a 3D object, and we project it onto a 2D surface. Now we know that this represents a cube because we live in the 3D world, and we are familiar with it. Now imagine a creature that lives on the flat 2D surface of the wall. So will this creature be able to comprehend the 3D object just from this projection? So that's Mr. Square from the story Dryland. So Michio Kaku says no, he cannot, because he can only perceive 2 dimensions at a time. So that would imply that we may not be able to comprehend the 4th spatial dimension. But there are objects that we can think about, the Klein bottle being one. The idea is that the bottle does not pass through itself. So it looks like it's cutting through itself, but it passes through the 4th dimension. And in case you're not familiar with this person, he's a famous physicist and writer, and he teaches at CUNY, New York. So that's about the hierarchical clustering methodology. And I want to make something clear that this is just about the processing part where you treat each variable as a separate axis. But in our physical world, temperature and pressure are not spatial dimensions, right? So they are properties of the system and we can sense and comprehend them. Let's move on to the results. So we'll look at some general features and then we get the variables for the hierarchical clustering. And not all variables we get are used in the clustering. So this is a vertical profile for a month for water vapor mixing ratio. So we have processed the data up to a height of 5,000 meters. But to focus more on the boundary layer, we will only look at up to 3,000 meters above boundary. So let's look at the winter profile for the mixing ratio. So as you can see, it's very dry. All the colors are in blue. And although the color chart goes up to red, we use the same scale for all the seasons so that it's easier to compare. And you can see the boundary layer top at the gradient, but again, this is a little hard to understand. The winter boundary layer is dry and stable because the cold air is at the bottom. And moving on to spring, so you can see the moisture rising as you approach summer. And in summer, there is higher moisture in the ABL. And there are a couple of reasons for this. Both of these sides receive more precipitation in the summer, and there's also the influence of the southerly winds that bring in moisture. So we have fall. So spring and fall are the transitional seasons where the characteristics are intermediate to summer and winter. So there's many days missing for Amarillo. So this is the data for a sample year. So one surprising finding, we had expected Midland to be drier than Amarillo, considering that it's mostly desert and it receives less precipitation than Amarillo. But when you plot the difference, Amarillo minus Midland, you see that a lot of the days the values are on the negative side. So this sample month, but for most months this shows like that. So it's probably because of the southern geographical location of Dryland. And now we look at some synoptic conditions. So the point is to say that there is day-to-day variability within the same site, and that's caused by synoptic conditions such as precipitation or frontal passage or dry line. And there is also difference between the two sites on the same day, even though they are almost on the same longitude. So they do follow certain general patterns, but day-to-day variability exists. So on the 1st and 2nd June, Midland is wetter at the lower boundary layer, and it's a combination of the precipitation and a cold front passage, and also the wind direction. So on the 1st June, for instance, Amarillo had northerly winds and Midland had southeasterly winds. And on the 10th of June, you see there is a Dryland present. So on the west side of the Dryland, where Amarillo is, it's drier, and on the eastern side, it's wetter. So we checked a few sample size to explain the variability. So these are the wind curves. You can see the change in wind direction. Next, the conditions are at the same site. So this is the water vapor mixing ratio for the month of September, and it almost follows a sinusoidal pattern. And we see a jump sometimes. Here, this jump in moisture. So where a tropical storm was sighted, and along with southeasterly winds. So that must have caused the increase in ABL moisture. And the cold front passage brought down the moisture because of the dry air addition. and the Dryland also brought down the moisture. And these box plots represent the water vapor median up to a height of 400 meters, and the green ones for 600 meters. So both within the boundary layer. And again, potential temperature. So with the cold front passage that we saw about from 21st to 22nd September, the temperature jumped by about 12 Kelvin. Next we come to the atmospheric stability using the Richardson number. So recall the formula. And we have potential temperature and the Richardson number along with the wind bars overlay. So you can see that this is a summer profile, and the purple ones are the boundary layer heights, and then it goes past 0.25, and then that's more stable atmosphere. But sometimes you can see it jumps back and forth. So it turned out to be not a very accurate measure of boundary layer depth or stability. We'll come to that. So in summer we have a higher boundary layer depth, higher maximum, and in spring as well. And next winter. So all the blue squares are at the bottom. This denotes low boundary layer, and this is a more statically stable atmosphere. So next, we found that the potential temperature and the mixing ratio profiles that were used to determine the boundary layer depth were more accurate than they are already. So we visually inspected the radiosonde profiles and then tried to match that with the programmatically derived boundary layer depth. And this is for the season of spring. So as you can see, the boundary layer, the BLD from the mixing ratio and theta, they are in good agreement. In winter, the correlation is a little lower, but all other seasons they're very much close and closer to the actual value as seen from the radiosonde profiles. So RIB, the correlation coefficient for RIB both the BLD from theta and mixing ratio, they are both not very high, and as you can see, RIB tends to underestimate the boundary layer depth. So I think this is because of the local maxima. When there is a slight difference in the temperature gradient, at the critical value, the first change in critical value happens, and then you underestimate it. So even if you exclude the surface inversions, it still underestimates at the higher boundary layer depths. Now we have a summary of the general characteristics. So we found the classical patterns of the wet, unstable, and deep ABL in summer, and the opposite in winter. And southerly winds do bring in moisture from the Gulf of Mexico, and then we discuss the high pressure node, and we see that effect. And other factors like precipitation, frontal passages, and drylands influence the ABL moisture. And RIB tends to underestimate BLD, and as we'll see later, that alone cannot be used as a measure of stability. And the correlation coefficient. Now we move on to the hierarchical clustering. So this is the technique. So we have applied the clustering to individual days. So we have one set of observations per day, which is at 0 UTC. And so we have 8 cases, one for each site and season. And from December 2015 to 2021, so that means we have 6 summers for one season. And several of these days were dropped because of incomplete data. And these are the cluster types. In every case, we noticed the presence of one large cluster, which is called the most dominant. And that was the largest and most representative of the season. And we have smaller ones ranked by size, the dominant and the least dominant. And I wanted to give them cooler names, but I was told that the journals might not like them, so we're sticking with these. So we will look at these profiles. So we have 8 cases, but we'll cover 2 of these for an MLO, summer and winter. So this is the first one. Yeah, so we have type 1 to 51 days, and then these 2. So it all says type 1, but it's 2 and 3. So now we look at the differences between these clusters. So if it's too small, from left to right it's type 1 to 3, and the first one is the mixing ratio. So you can see that type 2 has the highest mixing ratio, that is the most moist one, and type 3 is the lowest one. So if you look at the boundary layer depths for the same clusters, you can see that the type 2, which has the highest mean WVMR, has the lowest boundary layer depth, and it kind of follows the inverse pattern. So that shows some boundary layer dilution in summer. And the third one is temperature. So this is the air temperature, not the near surface temperature. So these don't change very much. I think it's because it's more influenced by the surface forcing. And we have soil moisture. So this was taken from not exactly the same site as the radiosonde launch, but the nearest available site from the West Texas Meson. But soil moisture does not seem to vary among the clusters very much. And initially I tried to use that as an input variable for the clustering, but that did not yield good results because it doesn't have much effect, but it somehow doesn't work with clustering. And now we have the dt over dt quantity. So we expect this to follow the boundary layer depth, and in summer it does. The higher dt over dt implies the higher boundary layer depth and the lower moisture content as well. And lastly, we have the potential temperature, so which in most cases follows the dt over dt pattern. So I'm not quite sure why it follows the temperature change. It could be related to the potential temperature is related to the temperature, and it is conserved in the boundary layer. So could be a reason. And now we look at the wind profiles. So for type 1, 2, and 3, as we saw above, the first one's hot, humid, and it has a deep ABL and southerly winds. So the southerly winds are associated with higher moisture in almost all cases. And then you have the next cluster, which is warm, and this is the most humid. So that is southeasterly. So that's what we expected to find earlier, but we see that even southerly winds carry moisture. So the wind pattern is a little distributed, but we're going by the most prominent direction. And the last one's the cool, dry, and the deepest ABL. So this wind from the southwest. So as we will see, we bring the dry desert air to our sites, and that causes the boundary layer to go. And next one, winter, we have this distribution of days. We look at the water vapor mixing ratio. So in winter, the variability is generally low, so you want to see a lot of difference. And the boundary layer depth is also, there's some variability, and even a few days where the boundary layer depth is very high. So I've checked a few samples, so it is usually due to a dry line or some other condition like that. So one of these clusters, type 2 or type 3, would have some atypical characteristics related to the season. So we have the temperature. So temperature is generally lower than the summer profiles. And soil moisture, not much variability, and the dt over dt. So in winter, it doesn't quite follow the pattern that we expected, but Yeah, so the slightly higher dt over dt corresponds to cluster type 3. So that is the highest BLD. And then we have the potential temperature. So we have the wind profiles as well. So we have southwesterly winds for type 1 cluster. So it's relatively warm, and it has, so here there is shallow ABL, which is not consistent with our other findings. Usually the southwesterly winds result in a higher ABL depth. And the northerly winds are, the finding from that is consistent because it's always associated with a dry ABL. And we have the westerly winds, which were found only in 2 out of the 8 cases. And there is also a deep ABL, and it's relatively cool and dry. And now we have some quantified data for the cases that we just saw. And there is description for each of the clusters. And then I also looked at the overall precipitation and the NCI weather type, just for information. So the thunderstorm weather dominates in the summer. So that's based on the most dominant cluster. And there were quite a lot of fog weather as well, and one case of smoke and dust weather. Okay. So we have the results from clustering. First is the relationship between the WVMR and BLD. So we expected the higher mixing ratio to increase the boundary layer depth. So it does increase if you check between summer and winter and other seasons too. But it's only about 160 meters. And spring had some of the highest boundary layer depths as well. And we saw the BLD dilution in the summer case. So out of the 8 cases, 6 of these had BLD dilution for the same weather patterns. And in winter cases, the variations were not strong. And next is the wind direction with the mixing ratio. So our hypothesis was that southeasterly winds were associated with the higher ABL moisture, so that is true. And southerly winds also contribute to the moisture. And northerly and northeasterly winds resulted in a dry ABL, so they originate in land and have dry air. And in addition, we found something else. The westerly and southeasterly winds also drive the ABL. So we also expected those to reduce the boundary layer depth, but these winds actually increased the boundary layer depth. Yeah, that's here. So westerly winds were found as a predominant direction in only 2 cases, and they made the ABL-B. And southwesterly winds were also always linked to ABL. So this is without the water vapor, it still makes the ABL grow. So we think this is because of the downsloping winds from the desert regions from New Mexico, Arizona, and the Mexican desert. And it could create an elevated mixed layer as well. And a few other studies found that dry air grows the ABL through the dry air entrainment. And next we have the dt over dt. So as we expected, generally high dt over dt corresponds to a high boundary layer depth. So it can generate stronger thermals because of the temperature difference, and not according to the absolute temperature. Yeah. But it's not always a perfect case in all the age rounds. And a couple of other observations. So as you know, higher temperatures are associated with a higher moisture content because of evaporation. And then the soil moisture variations were low, and only about 0.03%. So the previous studies have found the same. So the variation is weak in Drylands. And the final summary and outlook. We know drylands are important because it occupies about 40% of the land and it houses one-third of the population. And then we have the semiarid regions which are not studied enough. And we have studied the spatial temporal variability of the moisture in two sites for a period of 6 years and 1 sounding per day and 8 cases for the hierarchical clustering. And we already discussed the classical patterns. So in summer it's higher, the water content is higher, it's stable, and yeah. And next we found the effect of southerly and southeasterly winds, increasing the ABL moisture, and then the synoptic factors such as the precipitation, frontal passages. So these cause the day-to-day variability, and it also explains the outliers because some are not typical for the season. Like in winter, you have certain days with very high ABL depth. And lastly, we have the BLD estimation from potential temperature and the mixing rate. They are far better than RID. And we just discussed the hierarchical clustering results, the correlation between wind direction and DT over DT and ABL dilution. And I also spent some time trying to classify these bays just based on DT over DT. But yeah, I didn't find any patterns in this. So it could be because there's some missing information between the peak time, so it's sunrise, sunset, -4 hours, and then the sounding is after 4 or 5 hours, and so some changes could happen at that time. A front could pass. So it's not a very accurate classification on its own, but it was used as an input to the clustering algorithm. And for future work, we could add more sites and study more data, and other parameters along with RIB could be used to examine stability, because some previous work showed that RIB on its own is not a good measure of stability. Even a high positive value could be turbulent, and the choice of critical value is another challenge for various terrains. And lastly, we could use continuous measurement from a LiDAR to estimate the water vapor profiles and other variables to obtain a more complete picture. Okay, so I would like to acknowledge Dr. Sandeep Pal at Texas Tech University and our research group called BITs, and my advisor, Dr. Ankur Desai, and other GAC members, Dr. Chris Pujarik and Dr. Paul Stoy, and the lab members from the Ecometeorology Lab, and everyone at AOS, faculty, staff, students, the GSA for running the seminar, and our IT Guru Pete for all the support with technology, and family and friends. And that's the end of the presentation. Thanks for listening. And this is this is an image that I generated partly using AI. So the context is that this is a thermal. Yeah.
Questions from the audience, starting with students. Back. Sorry.
I never used this for scientific before, so maybe my question doesn't make sense.
Okay.
But have you tried to look at the temporal variability of the 3 types, especially with the goal of predictability, in the sense that maybe more one type, and then after 2 weeks of one type, you can have 2 days of something like that. Have you looked at that?
No, temporal variability as in day to day?
Yeah, each day, looking at the type of each day you go.
Okay, no, with respect to clustering, I haven't looked at that, but I did check certain samples, but not all the data points. So with that, I just mapped the general characteristics and the predominant wind direction and features. Yes, but yeah, that would be good to look at.
So do you think this kind of technique can be used to summarize the data in a very easily interpretable singular value.
Okay, like machine learning?
No, like this same thing. Do you think it's good enough
Mhm.
to summarize the data into one scalar value to be able to compare with only on one scale?
Okay, okay.
It's a good question, right? So can you use the clustering, right, as kind of a metric, right, like the variability of a time, and then like I
Okay.
think it ties back to your original question about, you know, how can you use this to improve numerical weather prediction models, right? So I don't know if you've had much thought about how you might like take this approach and then apply it to that first question you brought up. To build on
Right,
the last
yes.
question.
Yeah. A metric would be a good idea, yes. But yeah, no. And as for the weather prediction technique, yeah, no, I haven't actually worked on that, but just different weather regimes. I mean, I worked on WAT, but not on PBL schemes specifically.
Other questions? I was very curious about your lack of soil moisture variability, because it goes to my heart. My master's thesis was all about soil moisture variability driving southern Great Plains boundary layer depth.
Okay.
And at a different scale, it's more about spatial variability. But I'm curious, right? So is you're finding basically that, you know, the day-to-day variability in your clustering, which explains boundary layer variability, because it's not explained by soil moisture, is this basically just a regime that is strongly effective, or is it like that the local land-atmosphere interactions have a relatively muted effect on that, or kind of what's your thought process on that? Because to me, this is very counterintuitive, because the surface energy balance in a dryland system in particular is going to be strongly influenced by what's, how wet the ground is.
Right. Yes, it is. It should be, because the water availability should make the drylands sensitive to any changes. But maybe, yeah, the amount is limited.
So you're just saying because it's already low, that the variabilities you're observing are just not relevant for like boundary layer growth. That's a reasonable thought. Yeah. I've looked more in eastern, southern Great Plains where maybe there's greater variability. I guess everything was around 0.25 or so meters cubed per meter cubed. No questions, thoughts? Anything online? Well, if not, then let's thank Kiran again. We'll be here for at least a few more years, so feel free to bug him if you have other questions or want to talk about boundary layer ideas as we move on to some topics.